533. Today, Yasmin Abdenader, Samir Alam, Chen Jiang, and me, Calvin Zhang, are going to go over particle flow in sheep herding. As you can see in the GIF below, sheep are moving through a gate. Our goal of this project is to find the velocities of the sheep in various segments of the herd. To start out, we read the given 4 images into MATLAB. Next, we began our goal of isolating the sheep by converting it from RGB to gray. This makes it easier to isolate the sheep because we wanted to separate the sheep, which are white, from the background, which would be gray. We used a thresholding value of 153, or 0.6 of the maximum value of 255, to create a boundary in which values greater than 153 would be white values and values below 153 would be black. However, sheep were not the only objects that were marked white. The logo in the top right and the house were also white. To get rid of this, we simply cropped them out and set the values back to be black in their location. This slide shows our final pre-processed images. As you can see, the sheep all move toward the gate on the left as time moves on. Next, I'll hand it off to Chen for finding density contours.
So coming from what Kelvin was saying, here we're looking at the contour map, which is the heat map of the sheep before the erosion function was actually implemented. As we can see from each of the images from 1, 2, 3 to 4, before the erosion, the heat map was actually telling us some kind of degree of information, but not exactly. We can kind of see the transition between the density change from the center of the herd slowly move to the tip of the herd, but the change is not dramatic and not very obvious. So even though we are already moved all the elements outside of the sheep herd, there is still a lot more work we can do to make the density map more clear to see. And this is what we're going to do in the next couple of slides. We will, using an erosion function, and then magnify the change of the sheep, and then using the contour F function to displace the contour images in a more clear and a larger scale. So move on to the next slide. In the next slide, we're using our erosion function to make the pixel of each individual sheep smaller. So for each of these graphs, 1, 2, 3, 4, the erosion is implemented by using a structural element size of a rectangle 2 by 6. We actually successfully make each of the sheep of the size of a couple pixels. Some of the sheep will go as small as 2 pixels or even 1. So that's what we did to the individual sheep. As we can see in the graph, what we did to the overall herd is making the herd more clear to see the density transactions. Looking at the graph 1, the ones on the sheep that is not condensed in those areas, now it's more clear to see with a black background. And looking all the way to image 4, the tip of the sheep was actually shifting with the center to become the center of the density. So by successfully using erosion function, we can successfully enhance the density graph of these images. Move on to the next slide. So for this slide, we're actually using an inverse function, kind of inverse to what we did in the previous slide. We made the contour graph more clear to see, as we can see from pictures 1, 2, 3, and 4. The size of the sheep was actually magnified for the sole purpose of displacing the contour F function to make the image clearer to see. Something worth noting is, for the process purposes, we'll still be using the roster function instead of the density function. Here, for this slide, is solely purpose of using for the density map. So the next slide, we see that from after erosion, the density shifting is much more clear to see. From image 1, where the most condensed area of the sheep is towards the right down corner, and then for picture 2, slowly shift to the left. For picture 3, you can see a little bit condensed on the tip, and for 4, the density of the sheep was completely moving to the tip. This is to prove that our erosion was successfully implemented, and we can using this for later purpose for processing purposes.
So, as Leon showed us, before analyzing the images, we had to erode them so that each sheep can be represented by fewer pixels. And once that was done, we began detecting the movement of sheep from frame to frame. To do this, we used the function normxcore2, which computes the normalized cross-correlation of two matrices. The resulting matrix of this function contains the correlation coefficients. Before applying this function to the entire image, we first tested it on a small portion of the herd. As we see here, the left side is a cropped part of the herd, and we'll call this frame 1, and the right side is the same location but in frame 2. Within frame 1, we chose a small window, and we inputted this window and the cropped frame 2 into the normxcore2 function in order to find the resulting window in frame 2, which is represented by the blue box. Once we determined the functionality of the normxcore2 function, we created a for loop that traversed through the whole image and found the 2D correlation at different regions of the herd. We applied this step to frame 1 to frame 2, frame 2 to frame 3, and frame 3 to frame 4. So what I mean by this is, let's say we have the entire picture on the left, and once the for loop reaches the bottom part, it cuts out a small part of it, like we saw in 2 slides ahead, and within that small part we find the window, and then we use a normxcore2 to find that same window in the second frame, but also it's a cropped version of the right image. Once that is done, we use that window, we represent that window in respect to the full image. So we did this as a for loop from the peak of the herd, the top left peak of the herd, all the way to the bottom. And based on these results, we were able to calculate the velocities between frame to frame. In this slide, we see the results from image 2 to image 3, and as I stated earlier, we used the same for loop for each 2 images. So this shows the results for the same location as the previous slide, and we see on the left side that the window is slightly down, and when we compare it to the second frame, the window moved up a little bit to the up and to the left. The next slide shows us the difference between frame 3 and frame 4. Again, it's around the same location in the bottom right, and we see the slight movement of a frame from right to left.
To generate velocity maps, we use the quiver function. What the quiver function does is it plots arrows with directional components u and v at Cartesian coordinates specified by x and y. Because we already found these values earlier with the functions we created, making quiver plots was a simple process. We combined the velocity plots for the sheep at the gate and in the middle, and as a result, here are the 3 velocity plots.
To calculate the average velocity of the sheep, we took the slope value at each iteration within the for loop in step 3 and added the slopes to a sum. We then had to apply a threshold value for adding the slopes to the sum, since some slopes were calculated to be infinite in the case of sheep moving purely vertically. This is a trade-off we took for slightly less accuracy, as there were very few sheep that had an infinite slope, but resulted in a value that we could use in calculations. To help better visualize the results from our project, we decided to create GIFs of the images. We developed a method to create a GIF using 4 images and timed it such that it would display a frame every 1/25th of a second to mirror the frame rate of the original video. After trying the method with this frame rate, we saw that the GIF operated in a visually unappealing way, likely due to the fact that we were playing frames at the original frame rate without having all of the original frames, which caused rough transitions between the images. To fix this, we added a multiplier to extend the duration of each image in the GIF, which caused the GIF to have smoother transition between images while still retaining a video-like representation of the images. Additionally, we developed another method for the transitions between the images, as the previous method was hard-coded for 4 images and there were only 3 transitions. We increased the multiplier in this method as well, since the transitions were not originally from the video, which may be the reason why they required a longer duration to seem more video-like. Using the method previously described, we created the following 3 images. The original and eroded GIFs were created using the GIF creator method, while the velocity maps GIF was created using the transition GIF creator method. The original and eroded GIFs represent the direct motion of the sheep in space, and with the original recreating the original video, and the eroded providing spatial representation of the data we operated on to find the results. The velocity maps GIF is windowed to the most dense area of sheep near the center right, where we can see the sheep's velocity represented across the different transitions. As a general trend, from the velocity map GIF, we can see the sheep gradually change direction to having a majority velocity towards the bottom left direction, as also seen in the other GIFs.
Thanks for watching. We hope you found our methods for solving the sheep velocity very interesting.